Hello everybody, welcome to the Ultimate Physics channel. The topic of this video is thermal radiation, blackbody spectrum, Stefan's law and Wien's displacement law. The context of the discussion of this video topic is the birth of quantum mechanics. On 14th December 1900, Max Planck presented his paper titled On the Theory of the Energy Distribution Law of the Normal Spectrum. At a meeting of the German Physical Society. This date is considered as the birth date of quantum mechanics. Max Planck's paper was not taken seriously immediately, but the seeds for the birth of quantum mechanics were already sown. The subject of quantum mechanics developed over the next 25 years due to the work of several people such as Planck, Einstein, Bohr, deBroglie, Schrodinger, Heisenberg, Dirac, etc. Just like relativity, quantum physics is a generalization of the classical theories where the classical laws are special cases. Just like how relativity extends the range of applications of the classical theories into the domain of high velocities, quantum physics extends the range of application of classical ideas to the domain of the smaller dimensions. Just like how a universal constant, namely the speed of light c, characterizes relativity, so does the universal constant, namely the Planck's constant h, in quantum physics. One of the most important problems in the development of quantum mechanics is the problem of thermal radiation and blackbody spectrum. What is thermal radiation? Thermal radiation is the radiation emitted by an object due to its temperature. All objects above absolute zero temperature emit radiation to their surroundings and absorb radiation from them. Generally, the rate of emission is greater than the rate of absorption as long as thermal equilibrium is not attained. Once thermal equilibrium is reached, these two rates become equal. This idea forms the essence of Kirchhoff's law in thermal physics. Matter in condensed state, such as a solid state or a liquid state, emit radiation which is a continuous spectrum. Contrast this with the radiation emitted by matter in a gaseous state. The spectrum in this case consists of discrete lines called as the line spectrum that correspond to specified wavelengths. The general nature of the spectrum emitted by hot objects does not depend on the composition of the material, but rather on the temperature. At ordinary temperatures, objects are visible to us not because of the radiation they emit, but rather because of the light they reflect. If no light is incident on them, these objects won't be visible to us. As the temperature of an object is increased, it tends to emit radiation. At very high temperatures, objects become self-luminous. But even at temperatures of several thousand degrees Celsius, most of the radiation emitted by hot objects fall in the invisible regions of the electromagnetic spectrum. For example, if you heat up an iron rod, at low temperatures, it is hot but not self-luminous. As the temperature is increased, the iron rod turns dull red, then bright red, then yellow, then blue, and then finally blue-white. Thus, as we heat up objects, not only the amount of radiation emitted by them increases drastically, but also the frequency of the most intense radiation shifts towards the higher frequency side. In this case, from dull red to blue. The relation between the temperature of an object and the frequency spectrum of the radiation emitted by it is used in an instrument called the optical pyrometer. The optical parameter is essentially a rudimentary spectrometer that is capable of estimating the temperature of hot objects, such as a star, for example, by measuring the frequency of the most intense radiation emitted by it. Of the continuous spectrum emitted by such hot objects, the human eye picks up only the frequency corresponding to the most intense radiation in the spectrum emitted by such hot objects. Generally speaking, the details of the specific form of the spectrum emitted by hot objects somewhat depends upon the composition of the material. But there is one class of objects that emits a spectrum having a universal character. Such a class of objects are called blackbodies. A blackbody is an object that absorbs all radiation incident upon its surface. The name is appropriate since blackbodies appear black and they do not reflect any light when the temperatures are low enough that they are not self-luminous. One example of a blackbody is an object that is coated with a diffuse layer of black pigment such as lamp black or bismuth black. Any radiation incident upon the surface of such an object is completely absorbed by it. Another example is a keyhole drilled to the wall of an object containing a cavity. Let us see why this example is specifically interesting for a discussion of the blackbody spectrum. Any radiation that is incident upon the small hole enters through the hole into the cavity and fills the cavity. Due to the internal reflections within the cavity, most of this radiation is completely absorbed by the walls of the cavity. Only a negligible fraction of radiation can exit through the hole back to the outside world. Thus, the surface of this hole acts like a true blackbody that is capable of absorbing all radiation that is incident upon it. This example of a blackbody is more useful practically. In fact, most of the blackbodies constructed in laboratories to study blackbody spectrum are constructed along these lines. Irrespective of their composition, all blackbodies at same temperature emit thermal radiation having same spectrum. This general fact could be explained based on classical arguments of thermodynamic equilibrium. But the exact details of the spectrum could not be explained classically. The universal character of the spectrum emitted by blackbodies make them of particular interest, and physicists sought to explain the specific features of the spectrum. I have drawn the typical spectrum of a blackbody here. The spectrum of a blackbody is specified by a quantity called as the spectral radiancy, denoted by RT of nu, which is defined in such a way that the quantity RT nu d nu is the energy emitted per unit time between the frequency range nu and d nu from unit surface of a blackbody at a temperature T. Here these three curves represent the spectrum emitted by a blackbody at three different temperatures, namely 1000 Kelvin, 1500 Kelvin and 2000 Kelvin. One of the earliest accurate measurements of such a spectrum was performed by Lummer and Brinsham in the year 1899. The instrument used by Lummer and Brinsham in this experiment is essentially similar to the optical spectrometer used to study optical spectra, but the main difference is the lenses and prisms used in this experiment must be transparent to the low frequency radiation emitted by a blackbody. From these three curves we can see that the frequency corresponding to the most intense radiation shifts towards the higher frequency side as the temperature increases from 1000 to 1500 to 2000 Kelvin. And we can see that for a linear increase in temperature, this frequency shift is not increasing linearly. This is a very important feature of the spectrum. Curves of this nature are called distribution functions in physics, and we encountered many of distribution functions in physics. One good example of a distribution function is the Maxwell's velocity distribution function, which is basically a function that tells us in a system of gas molecules how these molecules are distributed according to their velocities. Another example of a distribution function in physics is the function representing the decay times of the radioactive nuclei. Another simple example is the grades obtained by students in a physics exam. These are some of the distribution functions that we are aware of. The spectrum of Blackbody represents one such distribution function where the distribution function RT nu corresponding to the spectral radiancy is plotted as a function of frequency, and that tells us how the energy is distributed across various frequencies in the spectrum. Let us discuss the specific features of this Blackbody spectrum. At frequencies nu is equal to 0 and nu tending to infinity, the power radiated is 0. And as the temperature increases from 1000 Kelvin to 2000 Kelvin, the frequency corresponding to the maximum intense radiation shifts towards higher frequencies. At low frequencies, the power radiated increases gradually and then reaches a peak value and then falls off at higher frequencies. The total power radiated is simply the area under this curve, which is given by the integral between 0 to infinity of this quantity RT nu d nu. So RT, the spectral radiancy, is basically this quantity. We can see from these curves that the frequency corresponding to the most intense radiation shifts towards the higher frequency side more rapidly than a linear relationship for the temperature from 1000 to 1500 to 2000 Kelvin, and this result was obtained empirically by Stefan in the year 1879 as RT is equal to sigma T power 4. And this expression goes by the name Stefan's law. Where the constant sigma is 5.67 into 10 power minus 8 watts per meter square. These three frequency values corresponding to the frequency at which the radiation becomes most intense, these values are denoted by nu max. That is the frequency at which the intensity is maximum. And we can clearly see from these three curves that this quantity nu max is proportional to the temperature T, and this relationship is captured in what is called as the Wien's displacement law. The same Blackbody curve, when it is plotted in terms of wavelength rather than frequency as a function of spectral radiancy, then we would be able to see that the wavelengths corresponding to the most intense radiation shifts towards the lower wavelength side as compared to the higher frequency side in this frequency spectrum. So if the same Blackbody spectrum is plotted in terms of wavelengths, we would have, instead of nu max, which is the frequency at which maximum intensity occurs, we would have lambda max, and that would be proportional inversely to the temperature T, and therefore we would have what is called as the Wien's displacement law. Lambda max times T is equal to a constant, and this particular relationship is called as the Wien's displacement law. Wien's displacement law, which is lambda max times T is equal to a constant. The constant here is called Wien's constant, has a value of 2.898 into 10 power minus 3 meter Kelvin. The displacement in the Wien's displacement law comes from the fact that the wavelength corresponding to the most intense radiation shifts towards or displaces towards the lower wavelength side as the temperature of the Blackbody increases. That is the reason for the term displacement in the Wien's displacement law. Wien's displacement law could be used to measure the temperatures of hot objects such as stars, for example, by measuring the wavelength corresponding to the most intense radiation of the spectrum. In fact, for example, for sun, lambda max is measured to be at about 5100 angstrom. This is for sun. And for example, for North Star, this lambda max occurs at 3500 angstrom. North Star or the pole star, which is basically Polaris. If Wien's displacement law is used by plugging in these values for the lambda max, one would get temperatures T for the sun at about 5700 Kelvin, and for the Polaris that would be about 8300 Kelvin. Thus, the surfaces of these stellar objects behave like black bodies, and Wien's displacement law provides a good approximation to measure the surface temperatures of these black bodies. The importance of Stefan's law and Wien's displacement law in the historical development of the subject of quantum mechanics cannot be overemphasized. That brings us to the conclusion of this video. Hope to catch up with you soon on another interesting topic. Until then, it's bye from me. Thank you.